Hi guys, this is a recording of section 10.7. This is on page 625 in our book, Power Series, and we start with the definition. Just to clarify, this video will be uploaded in YouTube, and whatever I'm writing, everything I'm writing on this screen will be uploaded in Blackboard. So you don't have to worry about copying down all of these things. You'll be able to just look at everything that I'm writing on the screen, and you could print it, you could transfer it to a PDF file, look at it on your phone, whatever you like. So, this definition is from the book. Definition states a power series about x equals 0 is a series of the form n equals 0 to infinity, and if we start replacing n by 0, 1, 2, and the list goes on, that's what a power series looks like, centered at 0. And here, where x is a variable, and the c sub n's, that is c sub 0, c sub 1, c sub 2, all the way up, those are constants, or simply the coefficients of the series. The coefficients or constants of the series. And this series, so this power series, converges or diverges. So this may converge or may diverge for some values of x. And later on, we're going to write f of x to equal this series. So far, this is what we have. Later on, we're going to actually write f of x equal this same series, and we're going to state the domain and the usual, whose domain is the set of all x for which the series converge. Rewriting, converge. Now, just want to note, this is my first video, so you might see a lot of imperfections. I apologize about that, but until I figure this out, this would be like my testing ground. Now, a series not centered at 0, so this is series. This is a power series, and we say this is centered at a, or x equal a, and it's right there. So it's identical to this power series, but instead of x, it's really x minus a. So this is pretty much what they're defining. For now, we're going to play with just what this means and kind of get used to it. And later on, we find a lot more than just the listing the series. So I'm going to take some problems from the book. We're going to look at an example, and directions state find the series radius of convergence and interval of convergence. That's part A. Part B, figure out for what values of x does the series converge absolutely and conditionally. So we're looking for radius and interval of convergence for which values of x is the series absolutely convergent and conditionally convergent. And this is going to be pretty much the majority of this section. I'd like to look at problem number 2. And problem number 2, and this is in our book. This is on page 633. So here I have a couple of options. That is, I recognize this from 10.2. We did this in 10.2 if you guys recall. And since I could write this a quantity raised to the n power, this is resembling a geometric series. So in this case, I could say, you know what, if I take the absolute value of r and set that to be less than 1, then this series is converged. Not only does it converge, it's absolutely convergent because the absolute value of that converge. And once I get this to be a positive 1, that number right there is my radius of convergence, which is pretty much the first thing they're asking for. And if I solve this absolute value, subtract 5 from each side, this would be my interval of convergence. So interval of convergence would be -6 to -4. Now, since I know, and this is of course absolutely convergent, so this is part B. Now, C would be none, since I know that since this is geometric, if r equal 1 or bigger than 1, this series diverge. So that pretty much sums up problem number 2. Now I'd like to look at another problem, and let me look at problem number 4. And number 4 reads, the series n equal 1 to infinity of 3x minus 2 to the n divided by n. Well, having this n is kind of messing things up for me because I can no longer say this is a form of geometric and say this is what r is. That's not true anymore. So instead, my only other options would be the ratio test or the root test. So in this section, anywhere they ask for radius or interval of convergence, and the rest absolutely or conditionally, I am going to have to use either geometric series if I could imagine that this is geometric, figure out what r is replaced by, and go from there. Or I'll use the ratio or the root test, and that works on anything pretty much. So here, if I take the ratio test, for example, the limit as n approaches infinity of the absolute value of a sub n plus 1 divided by a sub n, that would be the limit as n approaches infinity of 3x minus 2 to the n plus 1 divided by n plus 1. And instead of dividing, I'm going to multiply by the reciprocal. And we know from the previous couple of sections, we did this over and over. This is the limit as n approaches infinity, and wouldn't that be 3x minus 2 to the n times 3x minus 2 to the 1 over 3x minus 2 to the n times n over n plus 1, and we know this cancels out. And as far as n is concerned, this is really infinity over infinity. I could apply L'Hopital like we did, limit, or divide by the highest power term on the denominator, whichever you like. 3x minus 2, as far as n is concerned, is a constant. Derivative of the top is a 1, derivative of the bottom is a 1. So I am left with 3x minus 2. Now, since I'm using the ratio test, I'm going to take this and set that to be less than 1. This is absolutely convergent. Now, the author insists on this being a 1. So if I factor a 3 out of this, and have x minus 2/3 being less than 1/3, that's automatically my radius of convergence. And my interval of convergence is pretty much solving this inequality. And if I add 2/3 to both sides, that will be 3/3, which is 1. And that will be negative 1/3 plus 2/3, which is 1/3. This is my interval of convergence. This is part A. So far this is what I have. A states the radius of convergence is 1/3 and the interval of convergence is 1/3 to 1. Now, I am aware that in part B, since I used the ratio test, and this is less than 1, this is absolutely convergent automatically from 1/3 to 1. The one portion that the test cannot distinguish between whether it converges or diverges is when r equal 1, if you remember. And we're setting this to be less than 1. So what if we set r to equal 1? That means we don't know what happens with x equal 1/3 or x equal 1. We have to test those, and we're going to test them based on what we learned in the previous section. If I let x equal 1/3, and I'm talking about x equal 1/3 right there. If I replace that x by 1/3, that would be the series n equal 1 to infinity. 3 times 1/3 is 3 minus 1. 3 times 1/3 is 1 minus 2. That's negative 1 to the n over n. And what do we know? We know that 1 over n is positive. We're in agreement. 2, it's decreasing. That's true since n only appears in the denominator. You could just say that. And 3, we know that the limit as n approaches infinity of 1 over n equals 0, therefore converge by alternating series test. And if we let x equal 1, replacing this x by 1, 3 minus 2 is 1, n equal 1 to infinity of 1 to the n over n, which is a p-series diverge. So we're going to say this series is absolutely convergent from 1/3 to 1, and it is conditionally convergent only when x equal 1/3.